Phasors. Phasors are rotating arrows that can be used to represent the phase of a wave. Here we have the small arrow or phasor, and this will rotate anti-clockwise while we trace out the displacement of the head of the arrow against time, like this. We can label some of the major points of the rotation in degrees. So here the phasor had rotated through 0 degrees, and I'll put that on the graph here as well. Up here it had rotated through 90 degrees, 180 degrees, 270 degrees, and back here at 360 degrees. You see that the arrow or phasor rotates with the same frequency as the wave. An alternative method of labeling the angles would be in radians. So at this point the phasor has rotated through 0 radians. A complete rotation is 2 pi radians, and so here the phasor has rotated through pi by 2 radians. Pi radians, 3 pi by 2 radians, and then back here would be 2 pi radians. We might want to specify any particular angle, like this one for instance, which I can call theta. If the circle is of radius a, that is also then our phasor length. This distance here, the displacement of the arrow from the centre, is now given by a sine theta. The phasor completes 2 pi rotations, that is a complete rotation, in the time period capital T. So the angle of rotation theta is equal to 2 pi little t over capital T, where little t is the actual time and capital T the time period. We know that the time period is equal to 1 over frequency, and so we can substitute in to give angle theta as 2 pi ft. The displacement we showed on the diagram is given by a sine theta, and substituting in we can now get the displacement as a sine 2 pi ft. The phasor then allows us to specify the phase of a wave in terms of an angle theta. This expression is provided on the datasheet.